So here's the problem we want to solve. We've got a basketball. The coefficient of restitution, it's going to bounce. The coefficient of restitution of 0.85, and it's not. This is going to be like bouncing on ice. It's bouncing on a perfectly frictionless surface. Because in reality, if you toss the basketball, we're going to give it some horizontal speed. We're going to toss the basketball. If it were to land, it would at impact start spinning if it wasn't already as it hit. So we're going to hit the impact of frictionless surface. This is to make our life easier. We don't have to deal with energy going into spinning and what happens with that. It bounces on a frictionless surface, so there's no tangential force on the surface of the basketball. It doesn't spin. It just comes down, comes ballistically down, bounces, and comes ballistically back up. All right? No spin. Okay, so the basketball is going to head off perfectly horizontally, I'm generous, at 30 feet per second. It is. This is our ground here. It is 10 feet up. So the basketball is naturally going to follow the ballistic trajectory. It's going to come down here, and then it's going to come back up to some lesser height because it's not a elastic collision. Right? So it's going to come up to somewhere, if we were dropping it at 1 point, if this hit was 1.8 meters, this would come up to between our 1.2 and our 1.4 meters in height. So my question is, what are the angle of impact? So if we have the velocity vector right here, and we draw a line tangent to it right at that point. So we have this guy, and we've also got the vector as it comes off the surface. We draw a line tangent to that. Got that guy. And we call this theta 1. Angle. And we draw this, call this theta 2. My question would be, what are theta 1 and theta 2? What are theta 1 and theta 2? So, how would we go about solving? And let's do it the way that I know you can do once distance equals 1/2 at squared. I'm sure what you attempted to do with physics. As you saw in the last test, it doesn't work so hot when your acceleration isn't constant. So I'd like to run this through sort of my way, because while acceleration is constant in this, there's no guarantee that that's always going to be the case in future problems. Okay, so a lot of you, I got the impression, still graded the exams, I got the impression that a lot of you had trouble with this part of it. So, we're going to run it through, as I say, my way, where we start with the acceleration. We're going to run it through integrations to get the velocity and position. And that way, if you have a non-constant acceleration, the technique still works. Alright? Because one distance equals 1/2 at squared does not work with a non-constant acceleration. It does not work with a non-constant acceleration. Alright, so we have A of t. And it equals our negative 32.2 feet per second squared in the j direction. So I'm defining j is that way, j or y, and that's that way. Okay, so I'm setting it like coordinates. So that's the acceleration. The only acceleration out, we're ignoring air resistance and everything like usual. So our velocity, we're going to integrate this up. So v of t is going to equal, anybody? T. T per second squared j. Anything else? When we do an integration, we come up with a constant.
Plus the initial velocity.
And so our constant would be that guy. That guy right there. So yes. Initial velocity. So plus 30 feet per second I. Okay? And so now, so that's velocity. And then we want to know our position. So our position squared, divide the whole thing by 2. So feet per second squared. J plus, we're going to get this, so we're going to go from 30 t feet per second I, and we would have a constant again. When we do an integration, constant are a constant. I'm going to have to set my coordinate system right here. This is sort of my origin. The origin. And so my initial position, well, actually the origin is right here. Origin right there. Right below the basketball, right at the floor. So what should I add for my
4 feet J direction?
0 in the I, but we do have 4 feet in J. So plus 4 feet in J direction. Okay, so now, and this is true as it applies ballistically. It would change obviously post-impact. This is fine as long as we don't run into something. So we need to know when does this thing hit the ground. So it's going to hit the ground when our J position is 0, right? So we define where we define the ground is. So what we've got is got a positive 4, we've got a minus 32.2 t squared over t2. So we can just set that up, solve it out. So I have 4 minus 16.1, I'm just doing the division. This is feet. This is feet per second squared. T squared equals 0, which means, do a little algebra, t equals square root of 4 over 16.1 equals 0.498 seconds. That's how long it takes to travel from here down to the ground. And we're going to ignore the radius of the ball. We just say we measure the 4 feet here. All right. Okay? We're just doing center gravity. So now, what is our, how do we find our, remember what I was asking for here was theta 1. How are we going to go about that? So, what was that? It's the angle, so what am I measuring from here? I'm measuring from the ground, right? So like the x direction. And I'm measuring, yes, the velocity vector. So this line is tangent to the velocity vector impact. So I need to know, I know this direction. Got that one cold. But I need to know the velocity vector at 0.498 seconds. So I need to take v of 0.498 seconds. So v of seconds equals, sorry, negative 32.2. I'm running a little short of time, so I'm just going to skip to give you the answer to this. So it ends up equaling negative 16.04 feet per second in the J direction, plus our I is still unaltered at 30 feet per second I. Okay? So if I want to know the angle here, so I'm coming in with, so I'm coming in like the best velocity vector like that, and I know that this component right here has a height of 16.04 feet per second. And this component is the 30. And I want to know that angle, theta 1. I can take the arctangent of just the opposite over adjacent of the 16.04 feet per second over the 30 feet per second, and I x direction, remember we're bouncing on a frictionless, perfectly frictionless surface.
33%.
It's going to be unchanged at 30 feet per second. What's that? 5%? And it's not, the angle won't be, the velocity. So this, the next question is, what's this height right here? It's this distance. And so that, in order to determine velocities here, the coefficient of restitution is a relation between velocities. Okay, this is not, this is in feet, our units here are feet per second. This is not height, this is feet per second. We're doing the velocity vector, the angle between the velocity vector. So our units are feet per second. So this height here is going to equal our coefficient of restitution, so 0.85 times the 16.04 feet per second we came in with. And so that equals 13.63 feet per second. And so for theta 2, so this was theta 1 equals that. So theta 2 is going to equal the arctangent of this guy, 13.63 feet per second over the 30 feet per second equals 24.4 degrees. Any questions on any of this? Because I definitely would expect you to be able to solve a problem like this on the test. I will try, when we're doing homework, I'm going to assign at the end of Monday's class that we do next Monday, or we do next Friday. I'll go over it on Friday. We'll try to include a problem, includes this sort of stuff, so we're going to practice. Does everybody get how we're doing this? And so if I were to ask the same problem, and I say, we are on a spaceship in 0G, and our basketball has a thruster on it with a force equation of whatever, i.e. non-constant acceleration. Would everybody still be able to do the problem? If all it changes is right here, you're going to end up with, like in the test, you're going to end up with whatever. This A is going to be A of T is going to equal, I don't know. I mean, everything, I'm just going to do stuff based on time. I'm not going to screw with you based, I can screw with you much harder than that way. But it's everything be based on time. And I can say the acceleration equals negative 8t cubed. Say. Okay, I can say that. And so then when we do our integration, we go up to here, what's it going to be? What's the integration of this? So yes, Adam had it right. 4 plus some sort of constant would be our B naught.
AT to the 4th?
Yeah, B to the 4th. No, sorry, no problem.
Yeah.
Yeah, it's the 4th. Okay, and that constant is B naught. And when we integrate that again, it's going to be negative 8t to the 5th over 4 times 5 plus c to the t plus c2. Well, that's c1. All right, this is basic, super basic calculus right here. Right? Everybody accepts this is basic calculus that everyone should be able to do.